Welcome to 65th lecture. We have been discussing with DC machines, and we are discussing simultaneously the generating as well as motoring mode. And in our last class, last two lectures maybe, we found out the most important two formulas which will be used often to study the performance of a DC machines. And DC machine henceforth I will be drawing like this. As you know, these are the brass and this is the field coil, that is all. And field coil to be excited from a separate DC source when it is separately excited DC machine IF. And suppose when field current flows like this, the flux produced per pole is in this direction, this is called phi, and these two are armature terminals which will be like this. And these are the four terminals which will be available to us. So, if it is to be operated as a generator, I must connect a prime mover to drive the armature. Armature is on the rotor, mind you. And incidentally, just I would like to point out, in case of other rotating machines, the rotor winding and stator windings can be interchanged. For example, in a synchronous machine, AC machines, you can have field winding either on stator and AC windings on the rotor, or vice versa. It is equally true. Similarly, induction motor, you can give supply to the rotor terminals, stator terminals can be shorted and it will work nicely. But in case of DC machine, it is not possible to put the field on the field winding on the rotor and armature winding on the stator, simply because that this commutator actions, commutator and brass which makes DC will just not be there. With the advent of power electronics devices, very fast switching can be done, where such a thing is possible. Field winding on the rotor and on the armature winding, the mechanical way that we are rectifying the AC input voltage can be done with solid state switches if the armature is on the stator. That is of course outside the scope of this lecture. We will be conventional DC machines, field winding and armature winding cannot change their places, that is armature cannot be on the stator and field winding on the rotor. So, this is the thing, this is stator, always stator. Anyway, and we found out that the induced voltage, generated induced voltage across the armature we found out as Eg, if I write, it was equal to some Pz by A into phi into N. N is in RPS, and if armature carries current, then electromagnetic torque is Pz by 2 pi A into phi into Ia, where Ia is the armature current. And also we noted that if the machine is operating as generator, then there is a prime mover. Prime mover fixes the direction of rotation N, and electromagnetic torque which will be acting on the armature conductors when armature conductor carries current, electromagnetic torque will be in the opposite direction in case of generator. On the other hand, in case of a motor, motor mode, this is the brushes, and this is the field winding. Separately excited machine we are considering. If you excite this, there will be field here, flux per pole produced, and the armature current, if it is I A, then this will develop the torque, electromagnetic torque, and electromagnetic torque will decide the direction of rotation, and opposing load torque will be in the opposite direction, that is T L, like this. Got the point? Always remember this thing. Now, today I will first tell you that about shunt generator I will talk about. Okay. Before that, so generator mode and shunt generator I will talk about. Shunt generator. Will be the primary topics of today, but before that a separately excited DC generator and its open circuit characteristics must be understood very clearly. Okay? And there is another phenomena called armature reaction and its adverse effect, that I will take a little later. First, we rather go straight to a DC machine which is operating as a generator and as a separately excited DC generator. Now, so open circuit characteristics. So, first this is a separately excited DC generator. First we take this DC generator, means this one, this is the separately excited DC generator, clear. Achha, in this generator, suppose the armature terminals are open circuited, AC is off, there will be no armature current. With AC in open circuit condition, we are not going to load the machine. What we will do is this, we will change the value of the field current. We will make the circuit like this, connect a circuit like this, where there is a DC supply like this, plus minus DC. You should have a separate DC source, and then you make a potential divider connection, so that you can gradually increase the voltage from 0 if you put the rheostat variable point towards left, and if you connect an ammeter here, field current can be increased. So, this is separately. So, the characteristics of this generated EMF versus field current is called OCC, or open circuit characteristics. Okay, open circuit characteristics. And if I do that, the characteristics will look like, if the field current is 0, induced voltage will be 0. Phi is generally proportional to I f. So, as you go on increase the field current I f here, the generated voltage will increase and it will increase linearly at the beginning, is not. But after some time, as you go on increasing field current, the flux produced will not be in proportion to the field current because of saturation which will set in. So, what happens is this OCC characteristics is goes up and then take a bend like this. So, this is the open circuit characteristics. So, here you sketch field current and here you sketch the generated voltage E g. So, it will follow the actually the magnetizing curve of this BH curve sort of thing. So, this portion is the linear zone. So, this equation depends on phi, mind you, not directly I f. Phi can be replaced by some constant into I f provided the generator operates in this zone, otherwise not. Because if you increase the field current, the flux produced will become lesser and lesser. For 1 ampere increase in field current in the initial portion changes the flux by a large amount, but same amount of increase in current at this end will increase the induced voltage or flux per pole very little. So, this is called the saturation zone. Now, while carrying out the open circuit test, note down the field current and you connect a voltmeter here. And just plot them. Okay. But during this experiment, keep the speed constant. Speed, that is n, is kept at rated value. If it is a 1500 rpm machine, on the nameplate it is written, run it at 1500 rpm and get the open circuit characteristics. Speed n is kept constant while taking down this reading, then only it will be proportional to only phi. So, n is kept constant, speed. So, in this equation n constant, P z by A is of course a constant of the machine, phi depends on field current, phi depends on I f. And the relationship of phi and I f is linear initially, but later it is non-linear. Okay. So, this is the open circuit characteristics at certain fixed RPM, rated RPM. Now, if I ask you that what will be the open circuit characteristics, why it is called open circuit characteristics? Because I am not going to draw any power out of the armature, that is why it is open circuit, AC is open. If suppose I carry out the same experiment at half the rated speed, how the OCC will look like? OCC will look like lesser. I mean, in scale I have not drawn properly. What I mean to say, it will be like this. It is like this for a given field current. Here, suppose at this field current, this was the induced voltage at n rpm. If you make speed half, this induced voltage will also become half, that is, it will be here, got the point. Therefore, it will be like this, such that the generated voltage E g 2 by E g 1 will then be proportional to N2 by N1 at a particular field current at a given IF, because field current will decide flux per pole and speed is the factor. Therefore, one can easily get the OCC at any other speed he likes at speed n by 2. Similarly, if you increase the speed, OCC will be above this, like that. It is suppose at rated value, Okay. Now, on the nameplate of the machine, DC machine, some voltage will be specified. So, you increase the field current such that the rated voltage is reached. Suppose it is a 220 volt DC generator, 220 volt DC generator, and suppose this is the 220 volt. And the field current necessary at rated speed to generate 220 volt is this value. This characteristics only tells that you can ascertain or know the value of the field current needed at rated RPM to generate 220 volt if you have OCC at your disposal. So, this is the thing. We can now do the load test on this DC generator, that is, you generate this rated voltage, that is the open circuit voltage. Now, what you do? You start drawing power out of the generator. So, that characteristics is called the load characteristics, and how it will look like? Very simple. That is, I will go to next page and explain to you. So, we have got this no load voltage, this was the OCC, this was EG across the armature, and this is suppose the rated voltage, and this is the field current, that is the normal field current, and OCC whenever you draw you must specify at what RPM, at n RPS. So, this is about this, and what is the connection diagram? Keep it in your mind that this is the diagram which is relevant now. So, we are passing an IF here, and generator is driven at some RPM, NRPS, and here has the induced voltage V or EG, and then you have a switch to use the power which will be resistive in case of DC supply after all EG. So, with S opened, the load characteristics will be like this. Therefore, on this side I will sketch IA, and here I will sketch this V. I will connect a voltmeter here. So, with IA equal to 0, voltmeter will be this value, is not generated voltage, IF is maintained. So, open circuit voltage is this one. Now, if you close this switch, it will deliver current, and IA will flow. This terminal voltage, what will happen? It will be increasing or decreasing or remain same. It is expected it will decrease, because the armature has got a resistance. So, what is the equivalent circuit? Here equivalent circuit is armature. This resistance is very small, made of copper. Okay. This is R A, and here is your generated voltage E G, and here is your armature terminals, mind you, A1, A2, and here you have connected the load resistance R L. At that time some current will flow. So, this voltage we are measuring V then will be equal to terminal voltage across the load will be E G minus IARA, and minus there are some two brushes are there. There will be some voltage drop in the carbon brushes, and we write it as brush drop, which is little. Sometimes it is neglected. Generally what people assume is that 1 volt per drop and things like that. The reason for that is carbon brushes, no matter what is the armature current you draw, people assume brush drop is some 1 volt per brush, like that. Therefore, maybe 2 brushes are there, minus 2 volt extra, apart from the armature resistance which is inside this armature because of the armature winding. Now, the brushes are carbon, and carbon has a negative resistance coefficient, that is with larger current drawn from the armature, carbon brass will have lesser resistance because of temperature rise. Therefore, as if so what I am essentially telling, armature winding is represented by resistance over, but carbon brass cannot be represented by fixed resistance. Instead, what people try to find out, what is the voltage drop per brass, and that is the reason is the carbon brass has got negative temperature resistance. No matter what is the armature current you draw, larger current, resistance is smaller. Therefore, the voltage drop across the brass, which is resistance of the brass into armature current, that will perhaps remain fixed. That is the idea. So, some brass drop is taken. So, for our understanding, we can neglect also that. Okay. So, if brass drop can be neglected, the simple equation will be from circuit point of view, it will be E G minus I A R A. This will be the drop minus the small brass drop. IARA drop is also small. Therefore, if you vary this resistance, if you load it, means you are decreasing the value of the resistance, you are delivering more power, but at the same time terminal voltage will fall from this as you increase the armature current, and in fact, it will be like this way it will fall, and at a given armature current I A, load current, this then will represent IARA plus brush drop, whatever. It may not be a straight line nice like this because of brush drop present, but E g is this level minus IRA drop is your voltage now across the terminal of the generator. Like transformer, we can then say regulation of a generator, that is from no load to full load current. If it is full load armature current, IA full load to full load armature current, terminal voltage will drop by this amount. And regulation, as we know, we want a small value, a little change of terminal voltage should take place as you load the generator from no load to full load. This is how things will go. Remember that in this case, if you put a short circuit, that is RL is 0, then how much will be the current? So, with V is equal to E g minus IRA, it is like this, but suppose RL is equal to 0, means short circuited. If it is short circuited, then current will be very large. So, it is a separately excited generator, if armature is short circuited, armature current, which will then become equal to E g by R A. What is R A? Armature resistance, which is very small, that will be very large. I A short circuit will be very large, and if that short circuit current is allowed to continue, your fuse, if you have not connected any fuse wire for protecting this, it may burn the armature winding even. Okay. Therefore, short circuiting at the separately excited DC generator armature should be avoided. Like any other sources, why a battery, why should I short it? All power will be drained out, but in case of generator it is much more, it assumes importance because the armature winding will be at stake because of large current. Brushes may burn, things like that. So, these are the main points of a separately excited generator. You excite the generator from a separate DC source, run it at rated speed, adjust the field current so that rated voltage is generated under open circuit condition, then start loading the generator. But during this test, you must maintain the speed of the machine constant. That is, if speed changes a bit, it will in fact tendency will be, there will be a drop in speed because the prime mover torque and electromagnetic torque has to balance, and electromagnetic torque acts in opposite direction. For whatever reason, you have to always adjust the prime mover to maintain the speed constant to get these characteristics. So, this is called load characteristics. This is load characteristic and this is open circuit characteristics. Okay. So, separately excited generator are good, it is fine. at one time it was used, but only drawback of this generator is you want to generate DC voltage, but at the very beginning you are asking for another DC source. That is the problem. See, earlier to these power electronic devices, diodes, this that, DC generator was there, is not. Batteries were there, fine. It was not so obvious that in fact, people started with DC generation only, but only objection to this method is you require a DC supply. At that time it was not there. So, okay, this is nice, DC generator regulation will be better. Okay. I will discuss at length apart from this armature resistance drop to get the terminal voltage. Because of armature reaction, there will be an extra voltage drop, that I will discuss in the next class. Thank you.